Make something important out of that sentence. The slope is equal to twice its x-coordinate. What do you make out of that? y dx equals 2y. I also hope that you recognize that differential equation as something really famous so you don't have to do all the integration. What is it?
Exponential.
That's exponential growth. Y equals y initial e to the, normally I'd say kt, but in this case k is 2. So if you recognize that, then you saved yourself a lot of time. If you didn't, then I guess you got to do all that separating of variables and all that integration. The idea is recognize all three of those statements. If something grows proportional to its amount, if it has this differential equation, then it yields the exponential growth equation. You follow?
Nice.
All right. If the curve also goes through 1, 1, what does that allow me to find? The y naught, or the t? That allows me to find y naught. So 1 equals y naught e to the second times 1. Y naught is 1 over e squared. So your equation is y equals 1 over e squared e to the 2t. Yay? You with me? What else could you see as a multiple choice possibly? How else could they write that? Combine those. E to the 2t minus 2. Probably be more common. Okay? Okay, now, I believe Miss Cannon, yes.
Wait,
How did I do those?
Sister Rickman, can you do it the other way? Because I got bad.
Well, I changed the problem, so if you did it the way in the book, then it wouldn't be the same. So this is e to the 2t over e squared, and then I'm using the idea that if you have exponent, it's top minus bottom. Okay? Okay. Here we go. So I guess Miss Cannon taught you this already, sort of?
I don't remember anything.
Okay. So let's review then, or talk about this. I'll just teach it from scratch. So if I just asked you to average the numbers 88, 92, 84, 96, 90 as quick as possible, give me the average. Go. What's the average? Go. What?
Example
90.
You're going way too slow. Think
90.
faster.
90. 90. 90. Because they're all correlated. So you just do the middle one.
All right. So the point of this, I set this up pretty princess, but my goal is that not that you added those 5 numbers and divided by 5. My goal would be to say, well, shoot, but looks like the middle is
90.
90, and you would say this is 2 below, this is 2 above, this is 6 below, this is 6 above, and this is right at 90, so the average is 90. Now, wouldn't you say then that the average is such a number that the total number of overage and the total number of underage cancel each other out, and the over and under are 0, and basically the middle is found? You with me? So if you were to think of this graphically then, we said that 90 is, actually I kind of already showed it over there, but 90 is the middle, and we know that 88 is 2 below, and 92 is the exact same number above, and 84 is 6 below, and 96 is 6 above, and 90 is 90. All right, so then it seems like the total number of distance below and the total number of distance above should knock each other out, right?
Yeah.
Okie dokie. That's kind of a handy thing. You can average a lot of numbers mentally. I mean, I could average a class set of tests mentally by using basically this idea. You could just say, it looks like the average is about 90, and just take a running total of how much above and below, and whatever the off is. It's a pretty handy tool. That said, for calculus purposes, think of infinitely many lines drawn, so we'll get more like an area or a shade rather than just a rectangle. So in this case, I'll do one with you and then you'll do the rest. Given each curve, sketch where you think the average y value is and estimate that f at c or y value. So here, for example, obviously the y value is a lot of things going up from all the way like 17 down to 0. So what do you reckon the average value is? Average y value is probably
Half of that.
perfectly halfway in between, like this. Is that good?
No.
Would the average be a little above that or a little below that? Okay, so you want it. Oh, what the heck? I'll just move the graph. All right, like that.
Right.
Where do you want it? What are you trying to achieve there in terms of area?
Half above and half below.
So this, where the average is too small, should be equivalent to this, where the average is too big. Yeah, these need to be equal. Yeah. So ballpark, say we drew it there, then that means the average value, or f at c, is roughly 5. Okay, 5. All right, that's what I want you to do. Draw the line where you feel like the average y value would be in such a way that there would be perfect above and below area equal, and then estimate what that y value is. It is an estimate, by the way. It's not calculation. But I'm not sure. Call this -1. I don't know if that's what it is or not. All right, sorry, I'm slow. I'm just finishing. Oh, goodness. All right, ready? For the second one, Skylar, would you say f at c is about?
About 2.
Okay, I agree. Anywhere around 2 seems reasonable. Show, what'd you say for the third one? 1/2 positive or negative? Negative 1/2, I agree. That one I'm pretty certain of. There's good symmetry there, unless I should have cut it off there. What about the next one? Keegan, what do you think on the fourth graph?
About
5. I agree. F at C is 5. I forgot to call your attention to the directions. I want to go one better. It says, given each curve, sketch and estimate the average value F at C. So we did that. I also am saying estimate the X value at which the C is happening. So in other words, this is F at C. F at C is the Y value. C represents the X at which the average value is made. So anybody, what does the C look like in that fourth one? It looks like 3, eh? Okay. So you should be making 2 calls here. For this one, Mr. Becker, what did you say for the fifth one? F at C is about?
About 1.
Okay, I'm down 1. And if it's at 1, then you want to find the C value at which that happens. So what is C roughly, anybody? 1.1, 1.2, something like that ish. You down?
Right.
Last but not least, Katai, what's the F at C for the sixth graph? What? What'd you say? Oh, I am going to agree with you at one point, but isn't there a average Y value somewhere in here? Actually, maybe I do that wrong. So this, let me think about this. This is too much, yeah? And this is still too much, but now this is, over here it's too little and too little. So the Y value, I feel like the average Y value is 1.5, but now let's talk about that does not exist. You're right on the second part. When I say at what X value is the average value made, is there an X value that makes that average value?
Right.
No, there is no C that makes F equal to 1.5. Why not? What makes this graph different? Yeah, continuity. Or discontinuity, I guess I should say. All right, now that's actually the mean value theorem for intervals. We'll talk about that in a second, but let's go with the big idea. Obviously, I could put the formula up and say, here, this is how you find an average value. Do it, but that's not my style. So, sketch the curve 1 plus sine of x, please. One period in the first quadrant should be sufficient. Have something like that. Okay? All right. Now, would you pencil in the average value? Where do you think the average value will be? What do you think the average value will be, Ada? Okay? Drawing it at 1 gives you perfect match between area above and area below. All right. Now then. Here's where I want to develop the idea. Would you draw me that sinusoid again? And then draw me that red rectangle. Okay. At 1, 2. All right? Do you follow?
Right.
Okay, now let's talk area under the curve. How do the areas under those compare? They are the same. If I were to take, actually let's think of it this way. If I were to take this region, this area, and rotate it, and just fill that space, couldn't I take that area, fill the hole, and boom, they're the same, right?
Yes.
Okay, so we can agree that the area here equals the area there. Now the question is, all right, super, their area is the same, so what? Well, that's actually how you can find the average value. If let's see, is this right? No, okay. So if I were to take the area under the curve, let's do this. The area under the curve should equal the area of this rectangle, yeah? How do you find area under a curve generally? Forget the sinusoid now, just generally speaking. The integral from, assuming the interval is from a to b, then it's the integral from a to b of the function, yay? Right? And this equals the area of this rectangle. What's the base of the rectangle? B minus a for the width. What's the height of the rectangle? That's how, what is this y value? Well, that's f at c. That's the average value, right? Well, if you wanted to find the average value then, or calculate the average value, instead of trying to think, it looks about like this, you want to actually find it, nail it. F at c then is 1 over b minus a times the integral. So it really represents the area under the curve divided by the width of the curve, gives you that height of the rectangle that matches. That's where the idea of average value comes from. That's where the formula comes from. You should be able to use it to find the average value of a function. So, would you try this without a calculator? Find the average value of 3x plus sine of x on 0 to 5 and 2. You do not have to draw the graph, although it would be fun to do. What would the graph look like? Yeah, it would be like 3x plus a wave, yeah. It cleans up. I'm getting something like that. Do you agree with 2 over pi times the sum 3 pi squared over 8 plus 1? Okay, cool. All right. Let's then go to the unfortunately named mean value theorem for integrals. Now, it actually has a lot of logic to it. It's not just student torture. The mean value theorem for integrals, just by the name, gets confused, as you might imagine, with the mean value theorem. Generally, if you just say mean value theorem, it's implied there's some talk to derivatives. There is a mean value theorem for derivatives, which we talked about. There is also a mean value theorem for integrals. There is a relationship between the two. We'll get more in depth in that later, but it goes something like this. If a function is continuous, then there must be a c in a b such that blah blah blah. What does that mean? Yes. It has to have an average value and a little more. Okay, so go back to those graphs we looked at. Did they all have an average value? Everyone had an average value. Did everyone have an x or a point on the curve where that average value is made? No, that was the exception. The exception of the rule was this guy. Now, this one's continuous. There was an x that makes those average values. In fact, there were two x's, or two c's that made the average value here, right? This was continuous. There was a c. I remind you, c is an x value at which the average value occurs. This had two c's. It was continuous. This has a c. It's continuous. This has a c. Because this wasn't continuous, it didn't go smoothly from above and below the average. So we jumped over. This then would fail the mean value theorem for integrals because it wasn't continuous. That's why the continuity condition is there. So, with that said, if a function is continuous, there must be a place, think of it as x equals c, where the average value is made. I should say on the curve, where the average value is made. All right. So there are then some times where you're going to find the average value and just call it good. There are some times when you're saying, oh, all right, the average value, find it, but then tell me the x that makes it. That's what this question reads. I know it's kind of subtle and hidden in a bunch of mathy speak, but when it says given the function, find the c guaranteed by the mean value theorem for integrals, it means find the x equals c at which the average value is made. So start by saying, is f continuous? Is there going to be a c for this problem? Is this problem continuous? Yes, cubes are continuous, all right? So there should be a place where the average value is made. Now, I don't mind just calling it f at c for a second on the left side, but you do definitely need to focus, write yourself a note here. You're going to work both sides in a second to find c. All right, so f at c on the left, cool. The right side is the average value. All right, so how do I calculate the average value? 1 over 2 minus 1 times the integral from 1 to 2 of 2 plus x cubed. I remind you, in doing all this calculation, you're really trying to find this sweet spot in there, the rectangle idea, all that good stuff. All right, now, I can work the right side to find the average value, and I will. But I'm also going to eventually say, all right, there is some point on the curve c, so there's some 2 plus c cubed that equals that y value. So I actually need to consider when the function equals that y value, so that's why I mean work both sides. So working the left side means just replacing the function, and let that chill for a second while we finish the right side. What is the antiderivative? The 1 over 2 minus 1 is 1. 2x plus x to the 4th over 4 from 1 to 2. Again, keep the 2 plus c cubed for a second until we finish the right side. What do we get there? 4 plus 4 minus 2 plus the 4th. Wait. All right. 2 plus c cubed then equals, we got there 6 minus a 4th. Is that right? 6 minus a 4th? What's 6 minus a 4th? 5 3/4. Okay. 5 3/4, yeah? All right, now we're ready to start solving for c. What do we do? Subtract 2 and cube roots. Let's just do that together. Let's waste what times. So the cube root of, is it plus or minus when you cube root? No. Okay, so 5 3/4 minus 2, or cube root of 3 3/4. I should have made this cleaner so we could say if that makes sense or not, but I imagine it's one-ish. It seems like it makes sense. All right. Would you use your calculator to solve this question, please? This is a multiple choice question from the feed. And it's got a twist in there. Just like a lot of these questions, you have to kind of expect that besides the big idea, they might also throw a twist. What was it? Sine of 2x?
Yes,
Thank you. Was it 7 plus or what was
7
the
plus 9.
7 plus sine of 2x? All right. That's good. Now we need to get that together. All right, so I got my big idea. What now? What should I do next? Solve the integral? Find the average value? Okay, I will find the average value. Shift plus 7 to 8. Oops. 8. Did you get 7.5471 for the average value? Oops. No?
Yes.
Yes.
Okay. 7 point, I forgot what it was. 7.571? 547? 472. Okay, you do probably, at least on an AP test, obviously, they're not going to look at your work on a multiple choice, but on my test, I would expect to see some results along the way. How do I answer that question? Could I do it analytically, paper and pencil?
No.
It wouldn't be, so it wouldn't be great. I could subtract 7, I could get sine of 2x equals that. I could inverse sine of that, which I obviously wouldn't do, but I could take the inverse sine of 0.5472 and then divide by 2, right? All right, now that would be tempting and that would be fine. Obviously, they are requiring me to do more, so let's talk about this because this is a great gotcha question. There's still a trick in there that you need to be aware of. So you say, where is this 7.5472? How did you use your calculator to answer that question? Did you graph the average value? What did you do? You solved it? Okay. All right. So let's go here, actually. So you said you did the inverse sine of, shucks. The inverse sine of, what was it, 0.547 something?
5%.
Wait, what?
5472.
Oh, yeah.
And then you divided that by 2.
Yep.
Okay, and you got 0.289, yes? Okay, so your answer is
Not that.
0.289, and boom, there it is. Is that right?
No.
No, that's not right. What's not right?
Interval.
Yeah, you're supposed to find a region, an angle from 7 to 8 where that's made. And your calculator doesn't know you're looking from 7 to 8. The calculator is programmed to give arc sine answers from 0 to, actually negative pi over 2 to pi over 2. It's not going to find an angle from 7 to 8. You need to know how to find the angle from 7 to 8. So you could either add a bunch of periods, which would be gross, or you could use your calculator a little more wisely. What's another way to do this? Let's go to graph it and graph 0.5472 and, oops,
7.5.
oh, 7, the average value. Yeah, we need the average. My bad. Thank you. Find the average value, graph the average value. And now let's either set our window to 7 and 8 or, uh-oh, I didn't mean to do that. No, that's not right. I did not. Oh, now I can't get it. Yeah, there you go. That's pretty close. All right. So, I could set the window to 7 to 8, 7 to 8, so I only look in the correct place. Then, boom, I'm in business. Now I can find the intersection point. Do I give the x to the y? Is C, they're asking you to find the average value or the C at which it's made? The C at which it's made. So I give the x or the y?
Which one is it?
The x. So your value is, actually, these should be equal, yeah? Should they be equal?
No.
No, that's crazy talk. That shouldn't be equal. So that's why they're so close to equal. That's funky.
Because your line is
Bogus. So what did you say for your C? 7.5
5644.
is this one?
Yeah.
Okay. In terms of all the distractors, you can bet that the distractors are top flight on the AP test. So any intermediate response along the way, for example, if you agree that the average value is 7.5472, they are meant to get you to bite on stopping before the problem is done. So if there's some result along the way that you might get, it'll be there. And it's for you to know, I need to do the whole problem, not bail early, so don't bite on the average value. This was meant to be a range question, so the distractors are good is my point. All right, last but not least, this kind of average value idea occurs a lot in the responses where you do some writing. So imagine if I told you that the number of problems a student has to do at any time since the first day of school is given by this function. So this graph feels like it's going to be increasing and decreasing, increasing and decreasing. Why would it increase and decrease? Because
The sinusoid.
that's true, but in terms of the number of problems, why would it increase and decrease? Because every day you do some and I give you some. Okay, so you're doing some and I give you some and I give. So you're in a constant state of doing problems. Yay? What is the most a person would ever have to do at a time? You should be able to look at that graph and know
I wish it
the
was
most they ever have to do is
I wish
15 and the least they ever have to do is
11.
11. So it's probably not a great model. Maybe it's not a model for this class. But anyway, you get the idea. Would you find and interpret, innovate? Find, innovate, and interpret it, please. I can't imagine you need a calculator for that. When you say, it means you don't remember your trigonometry.
It's true.
13. Okay? Interpret.
I got it.
So anytime you interpret, you should say when it is and what it is. So at t equal 8 days, this what? What does n represent?
The student has to do 13 problems.
Yeah, the student has 13 problems. Right? Okay, now find and prime it, please. What was your value? I got pi.
I got pi.
Okay, now interpret. Now, when you go to interpret a derivative, first couple of pointers. It helps to dump prime notation and think instead Leibniz notation. So think dn dt to remind you that a derivative is a rate. Second, anytime you interpret a derivative, we talked about how you should always interpret the sign. So in this case, what do you make out of this? At, and it is and what it is. So at t equal 8 days, what's going on? The number of problems the student has to do is increasing. Number of problems to do is increasing at a rate of pi what? With units.
5 problems.
Pi problems per
Day.
day. It's a rate. It needs to have rate units. Problems per day. Okay?
How do you get the problems per day?
Say it again.
How do you?
It's an average. Can averages be not a whole number?
Yeah.
Sure, yeah. Okay, so it's good. All right. You may use a calculator for the, do you need a calculator?
Nah.
Nah. Integrate this by hand. Surely we can integrate this by hand. Sometimes you do stuff you don't want to do.
I just kind of, you don't want to do it either. So am I.
No. Minus 2. Okay, so percent cosine. So I don't know if you're gonna legit use sub or mental use sub, but that pi over 2t is a bit of a sticky wicket, so be careful. Oy. Now I'm regretting this. 26. I could have thought through this. Oh well. That's all good. It's all good. All right, so 4, 5, minus 4, 5. So it is.
Yeah, 13.
13. What would that imply about 2 to 6? It's either a full period or 2 full periods, or it's got to be some perfect full cycle, so above and below is canceling, yeah?
Aye.
All right, so now let's interpret. At time equal 6, or at time equal 2, or over the interval. Over the interval, or something like from time equal 2 units. Days to time equal 6 days. What? The
Average value was 13.
the average number of problems
You had to do.
the student had to do was 13. All right, so interpreting an average value. Now you can see that this not being 1 over 6 minus 2 then makes it a little subtle. Okay, 1/4, what? You have to remember that that's kind of simplified. So that comes from 1 over 6 minus 2. It's an average value, right?
Yes.
Okay, that is the exact same problem.
Yeah.
Okay, let's see if you understand. Now do it again. That's it. I think we're on to homework. So you have the yellow fun sheet with staple, yes? It's not a packet, it's a fun sheet with staple. So let's see how you did. I'm on page 2. I think we did page 1 in notes, right? Page 2, number 1 is B. Well, I'll give you the answers and we'll go back over questions later. Number 4 is C. We. Number, okay, so the first one was just meant to, just kind of common sensey. We didn't get into the calculus. You pull the cake out of the oven, assuming the cake was the same as the temperature of the oven when you pulled it out. It was 400 degrees when you pull it out of the oven. When does the cake cool the fastest?
When it comes out of the oven.
Right at the start, when it's fresh out of the oven, at the start, or time equals zero. Okay? This also, we haven't done the graph for this yet, so it's kind of thinking it through. At time, we know it starts at 400, and if the room is 70 degrees, the cake will approach the temperature of the room. Somebody asked Mr. McKellips if the cake would affect the temperature. Would you, actually, I'll just ask you, AP Physics people. Would the cake affect the temperature of the room? Would the,
Technically, yes.
Yes.
it would?
Technically, but it's irrelevant.
Okay. So what would the shape of the graph be? The cake This is why I don't ask physics. Depends on how you define
There's no friction.
So are you see,
The table is the friction.
never ask physics. Never. All right. So it looks something like that, yeah? Okay. Now, what I'd like you to understand then is how Newton's law of cooling works. Newton's law of cooling is actually starting from not, so he didn't just say, here's a temperature equation. He actually said, I understand how the temperature will change. Not how the temperature is, but how the temperature will change. So he actually started with a differential equation for how the temperature is changing. And he said, it's my theory, that the rate at which the temperature changes will relate directly to the difference between this is the temperature of the cake, and the temperature of the room. Now, what I was shooting for in this equation is that you actually confirm that this makes sense with what we think. So why would it cool the fastest? Fastest implies that dt is greatest then, yeah? Are you with me? I guess the biggest negative is really what I meant to say. Well, when would this be at its greatest? If this is great, then that means this is great. When is this great?
At the start.
When this difference is
The biggest.
as big as possible. So the rate of change would be greatest when the difference between the two, the difference in temperature is greatest. And surely that would be at time 0, because that's before the cake has started to cool, yeah? Likewise, this side also makes sense. Tell me why that part of the graph makes sense. As time of the cake approaches, come on, talk to me, people. Time of the room.
Temperature?
I'm sorry. Oh, now I understand why you're confused. As the temperature of the cake approaches the temperature of the room, then the difference between the two approaches 0, and so the rate of change, or the slope of the curve, approaches 0. I mean, the difference relates directly to the rate of change, so it makes sense that the graph flattens out there. Yay? All right, without finding k first, will it be positive or negative?
Negative.
Why?
Because it's exponential decay.
So it's decreasing. So what? So the derivative should be.
Negative.
How do you know that's not negative?
Because it's
Because
not.
it's positive.
Why is it positive?
Because
Because
400 minus some.
because the
value
cake
is
must be greater than the room. Because T is greater than the temperature of the room. So T dt can only be negative, which it is because temperature is decreasing. Because K is negative. Something along those lines. I imagine a lot of people just say it's negative just because it is.
because cake is good.
Yes. My temperature equation, let's see how you did. My temperature equation is 70 plus 330 e to the natural log of 23 over 33 all over 4t. Did you win? Okay. All right. We might have to go over that tomorrow. We're not going to have time for that. What about the next one? What'd you say for an answer? D. Back page. Oh, shucks. This one will require a little more time also. Oh, we did this. Oh, we did the first one, but not the second one, yeah?
Yes.
Okay. So, A. Did you get an equation? Did you show the derivative gives the slope and then give me y minus 2 equals 8 times x minus 1?
Yes.
Okay, B, did you get an estimate of f of 1.1 is approximately 2.8? Okay, were you able to tell me if that's an over or an underestimate? Under. The estimate is, what does the question say? Is this approximation greater or less than f of 1.1? Less than what? Okay, so now the question is, did you say it well? So did you say something like the second derivative at or on the interface? So this is actually a fine point. We're not going to get to it. Is it enough to say it's concave at the point of tangency? Or does it have to be concave up or down from the point of tangency to the point of less? I'll let you think about that, and we'll finish going over it tomorrow. Keep this till tomorrow, and our homework is 89, which you should mostly have done already, yes?
Yes.
I got like 5 minutes to get a second. Like, this project, I was like, yo, it's just one. Why throw it away?
Everybody see the show tonight or this weekend? Yes.